Hello everybody, today we're going to look at the introduction to quadratics. Now I love this problem because it gives us an application that we can use, and when we actually build the equation, this actually makes a lot of sense. Okay, so the task is writing a quadratic model for maximum area given a perimeter. This is a classic problem. So for example, let's look at this Fence Me In company. It's a business that specializes in building fenced enclosures. One client has purchased 200 feet of fencing to enclose the largest possible rectangular area in her yard. Okay, so our goal is to figure out what that maximum area could be. Now, when we start looking at a perimeter of 200, just draw a diagram here for us, we start to notice pretty quickly that we can come up with all kinds of examples here. This one, let's start us out with a width of 80 and a length of 20. And you may say that's 100, that's fine, but remember rectangle has opposite sides that are congruent. So in this case we have two 80s, which makes 160, and two 20s, which makes 40. That would give us a perimeter of 200. Now the question is, what would be the area for that situation? So a lot of times, if we don't know where to start building our model, we start thinking about all the possibilities, and it becomes overwhelming. So here's an example where I've given you four examples of different rectangles that are all different shapes. So we're going to get different areas here. But we can come up with these four rectangles that have a perimeter of 200. So we quickly are overwhelmed with possibilities. Let's look at it, how we could maybe organize our thoughts in a table. So here are some examples. The first one I gave you, 80 and 20, that would give us an area of 1600 because we're going to do length times width. We could also come up with 60 times 40, which would give us an area of 2400, and also 90 times 10. So that'll give us 900. Now it's important to note here, our table, we're not listing two lengths and two widths, and we'll see why here in a second, why that simplifies things. Because those are equal, the two lengths are equal and the two widths are equal, we can list them out like this and start thinking about possibilities. Now if we consider decimals and fractions, we actually could come up with an infinite number of rectangles for this situation. So our next task as we look at this is, what is the relationship between the length and width for this rectangle? And so if we go back and look at our table, if you notice, if we add up our length and width each time, what do we get? Well, we get 100, which is basically half the perimeter. And that makes sense because we're looking at half the perimeter for one length and one width. So if we add L plus W, we get 100 every time in this situation. So after we have an expression for the relationship between length and width, our next task may be, write an expression for the width in terms of length. Now this is typically difficult for students to comprehend, but when you see the statement, when you see in terms of length, that means you need the length over here and an expression for W. So I'll just highlight that for you real quick so you can look at that, take that down in your notes. So we have this situation right here, and we're going to see why we rearrange this equation here like this in just a second. Okay, so our next task is write a function a of L that models the possibilities of area given length. Well, the first thing we notice when we think about our a of L, so we use our relationship L plus W equals 100. The first thing we notice in this equation, a of L, and this is kind of like a y, so think about a of L as a y. Notice we have three variables here. We have y, L, and W. And that's not something that we're going to be able to graph on a piece of paper or on Desmos or on our graphing calculator because it's got three variables. So we need to simplify the situation. So we're going to use a little trick in algebra, and this is why I like this problem so much. We're going to kind of make a substitution here in just a second. So if you can see, once we solve this L plus W for W, remember what we did, we said W equals 100 minus L. So this piece over here actually, oops, if I can get my screen to cooperate there, this piece right here actually equals W. So if we plug it into our equation, notice what we get. We get something with just two variables. And the two variables I'm talking about are a of L, or remember function notation, that's the same as y. It stands for our area. So that's one variable. And then we have this L over here. And this is something that we're used to working with. Now you're used to seeing it in terms of x, so I'll put this up here as well. We can use x when we go to graph it. We're going to graph it in just a second. So here's our a of L equation. A of L equals L times 100 minus L. Now make sure you're using parentheses here. That's very important because that L will get distributed if you were to write it in standard form. Okay, great. Okay, our next task is going to be to graph this equation. And so I put it in y equals here. You can see on the calculator. Put in x times 100 minus x. And then when we hit graph, watch what happens. So I'll bring up the graph here. Now I'm starting with a 10 by 10 window. And what I notice here is I'm just seeing part of the equation. What I should be seeing, since this is a quadratic, we should be seeing a U-shaped graph at some point. So what we need to do is set our window accordingly so that we can match this. Now notice that when we looked at our table, we did find an area of 2400. So we know we need at least, so if we go to our window settings here, we know we need at least for our Y max, at least 2400. So I'm gonna go a little bit higher than that. Let's go 3000, and that'll make sure that we see that 2400 because we may have an area bigger than 2400. Remember, that's our task, is to figure that out. So for my y-axis, I want to go from 0 to 3000, and then thinking about the lengths possible. Remember, our whole perimeter was 200, so there's no way we could have a length that's greater than 100 because that would be half of the total perimeter. So we're going to set this to 100 and see what happens there. So remember, x represents our length and y represents our area. So now that we have a good window to work with, let's go make sure that works. And it appears that we have a nice window there. And we're going to need to understand what's going on with the graph. We have our length is on the x-axis where my arrow is pointing, and our y-axis represents the area. So if we're looking for the maximum area, we're trying to find that spot right here. So I'm going to share a little calculator trick with you how to find that. So if we go second, trace, you can follow the red buttons over here, and we pick maximum right there, and then it's going to ask us some questions. It says, what's the left bound? Well, that means my cursor needs to be left of the maximum. It just has to be a little bit left of it, and then hit enter. And then I need to scroll right because it's asking me about a right bound. So I go to the right, and I hit enter. And then it's asking me to guess where the maximum is. That's kind of neat. It's doing some calculus here for us, so we don't have to do that. We're going to let the calculator do that work for us. And we notice right here, the maximum area is 2500 with a length of 50. And if you think about that, if we have a perimeter of 200 and our length is 50, that means every side is 50, giving the square as our maximum area. And that will always happen with these rectangular problems. So let's return now. We're going to return now to our prompt here in our PowerPoint. I'll be right back. Okay, so our next task is, what is a reasonable domain arranged for this function, A of L? So we're going to look at what we have for the graph. This is what we just did, right? And notice sometimes the calculator will give you an approximation to the length. We're going to round that to 50 if you ever see that. This is a graph I made earlier on it. Sometimes it does, sometimes it doesn't. Depends on where your cursor is in the window. So what's a reasonable domain and range? Well, remember our axes here. So let's just kind of label what we have here. Remember, this point right here was L equals 100 because we set up our window like that. And of course, this is L equals 0 up here. And remember, our area went up to 2500. That was our maximum area. So as we look at our domain here, I brought it in with the official inequality notation. Our domain in terms of length goes from 0 to 100, and our range is going to be our area, and that's in terms of A of L. And that's going to go from 0 to 2500. So I hope this instructional video has helped you with your math today, and I'm going to conclude that and bid you a good day. Take care.